Yeah, cool. Sorry, just muted on the Zoom. All right, so we did this little preamble, talked a little bit about history and brief introduction to how you might start representing. Like we're working with bits. I said a little bit about a Turing machine. At this pile of abstractions that we're dealing when we're dealing with software, at the bottom, it's this low-level logic engine that can do logic really, really fast, like billions of times a second. Kind of blows my mind. Remember, computers were in the megahertz when I was a teenager, and now they're up to gigahertz and multiple cores and crazy stuff. So it's just doing logic as fast as it can. So us as humans, we're trying to talk to a computer at this low level using these things called programming languages. We want to represent things we're interested in as humans, natural numbers being the starting point. So natural numbers, we model these, most typically model these with unsigned integers up to a fixed level of precision. Then you go the integers, there's a signed int. There's this slightly kooky representation for signed integers. That's a little bit strange. This is where I probably lost a few people of going into why you might do that. We're talking about this ripple adder circuit that I've implemented in Julia, but we'll come back to it. This is just like for your edification. Like, I wouldn't expect you to know this stuff. It's just like nice to know at the beginning, but it's probably a lot if you're just coming into it. I understand that. The whole point, signed integers, unsigned integers. Signed integers have this funny 2's complement representation because you get to use the same hardware underneath for addition. That's the main reason we do it. And this is like something someone actually discovered. It's like a thing someone worked out in the 40s or 50s. All these clever people trying to work out, like in the evolution of computers, they didn't do this all the time. There has historically been different representations of these things in memory on a computer. Okay, so talked a little bit about hex and doing bit shifts. There's like a quick way of doing division and multiplication by 2, bit shift to the left, bit shift to the right, because we know binary is this representation of powers of 2. Okay, and a little bit about how big in memory some of these basic data types are. Okay, it's a lot to start with, I understand. If anything's not clear, come and talk to me. I saw someone linked a cool video on the Ed thing about 2's complement stuff. I think that's cool. If you want to go and watch that, I encourage that. Okay, so we're going to start a bit more from the beginning. Again, go back to the beginning. So we ramped up, we'll go back down. Introduce with simple hello world in Julia. Then today I'll probably spend most of the time, I'll see how I go with time, but most of the time talking about how do you get a computer to take a square root of a number? Like this is this thing I was showing you, this book with tables, like, the one here was just division, but in a funny base because it's pounds, shillings, and pence. But these tables of logarithms that people used to have, tables of trigonometric functions. I don't know if it's clicked to any of you, like computers got to work this out somehow. How does it actually do that? And we'll go through a simple example of how to do a square root. And then there's kind of an interesting excursion at the end of how you might calculate the reciprocal of a square root. It's called inverse square root. It's not the inverse, it's the reciprocal of a square root. Because often when you're dealing with these things in practice, you don't actually want a square root, you want an inverse, one on the square root to do normalization. That's where we'll go. Cool, that's the prelude. I'll just start going through it. So, as I said yesterday, has everyone, where am I going here? Yeah, start a new one. Okay, so most common way to interact with Julia is in the REPL. Typical thing you do first time you're going to learn a programming language is historically do a hello world program. It's like really easy in Julia. It's just start a REPL session and go print hello. That's all there is. That's the easy way. The biggest thing is like how you interact with it. Like if you're interacting with Julia from the outside of a REPL, or you're trying to make like a program that other people are going to use, it's a little bit more complicated. I'm sure when you'll get more to that later in the course, we'll talk about that stuff. But if you're just hacking around, which like we are at the start of this, you'll typically go to a REPL session. Another one you might go to when people are using Python here, where they're all using Jupyter notebooks. People like notebooks. Anyone not like notebooks? Anyone not use the notebook? You've not used the notebook before? Oh, well, you get to experience that. It'll be fun for you. So there's a package in Julia called iJulia. Let's go using iJulia. If you don't have that module, it'll give you a prompt to download it. None of the ones I've done this, I did that because I didn't want it to crash out on you, crash out while I'm doing the lecture, but in case anything went wrong. But typically, if you're going to go, I'll just do an example. So using, here's a module I probably don't have in my path. It'll give you this prompt of like, oh, you don't have banded matrices. Do you want to download banded matrices? And if you want it, you go yes, and it'll do the download, but I won't bore you with that. There we go. So didn't do it because I didn't download it through that error. So, yo. A bit small, okay. How's that? Can you see that? All right. Cool. Yeah, so one thing I'll say, you see this in here, I think I saw someone already with it. You get fairly arcane errors in Julia. I'll admit that. Like the errors you get aren't super helpful all the time. It's one of the things with a young language. It's going to be better in the next version, I swear. When 1.10 comes out, it's going to be actually good. But I understand that they're a little bit cryptic. You do get good at deciphering them after a while. So if you get a message, you get some red, don't understand what it is, please feel free to chat it to one of the lecturers or the tutors, and we'll be able to help you out really quickly. But that's the thing. So using iJulia, iJulia has a little function called count type. Notebook. You don't need to do this because it gets exported into your path. If you do notebook, it'll start up a kernel, a Jupyter kernel. So you'll click on something like new, you can use Python. So Jupyter is like Julia, Python, and R, I think is what they originally were making this thing for. So that's where the name comes from. You can choose the backend, so you can use old Julia, Julia 1.9.2 or Python 3 if you want to do that. Some people really like notebooks as a way of working. I personally don't, for a reason that's probably a bit cryptic at the moment. I'd say it's like implicit global state. It's hard to tell what's lurking around in your notebook and which order you've executed the cells in. That can lead you astray. Sometimes it's easier just to kill the notebook and start again. That can be quite annoying. But this is another way to interact with it. So you can go X, 1, 2, 3, Shift Enter. We can do something like sine of X. All that stuff. You can do plots. Same, so you can have these cells. It's like having a little workbook to work through. Lots of people like working that way. Lots of people in data science love it. Personally, not a huge fan. I think write functions, make modules, have everything programmatic so you can get through it. So they're the two main ways you probably interact with Julia at the start of this course. It's like notebooks if you want. I think in your homework, you're supposed to be doing notebooks. Yep, so cool, you don't get a choice. You have to learn to love notebooks. But me, I nearly always go to the REPL and always go to a code editor. And but we'll talk about that in a little bit later though. So they're the two, I'd say that's the two main ways of interacting with these things. Now it's stolen my focus, as it does. Oh, what are you doing to me? Yeah, so we'll do a bit more Julia mucking around. So I'll just kill this session. Control-C. Okay, so we've got a couple of examples. So arrays, yesterday I would have been showing you like an array of integers, 1, 2, 3, 4. We talked about integers as a type. So I'm going to keep saying type. I probably haven't defined what it is, but you get used to it by just me saying it a lot. And then when we get further on in the course, Andy will go into a deep dive about types and why you might care about this stuff. Modeling, human problems in code, types are a big thing. There's other different types of I'll talk about that later. I won't talk about that now. You can have, this is an array, you can have an array of different types. So before I was just saying X equals hello. And I told you this useful function yesterday, type of X is a string. I can print a string, but I can also make an array of strings. So hello, everyone. So that's an array. If I go type of X, It's a vector of string, and in little dark gray, you might not be able to see very well. It will say that's a type alias for an array of strings. Cool. I don't know what other little examples we've got here. We're just showing some basic syntax for for loops. So we can go for I and 1 to length of x. Try not to get mad that Julia's 1 based. So you get used to it. It's got a historical precedent in Fortran. So in scientific computing languages, they like 1 based. I don't know why they picked it for Julia, just to make a lot of people mad, I think. So you can go through this and go print x I. So in this, put the square brackets. Square brackets are for indexing into the array. Round brackets are for calling a function. So print is a function in Julia. I'm passing it this variable x element I. It'll go through my array and go, oh, without a new line. So I didn't have a new line, so it's just printing it all in one go. Hopefully in the notes, we were a little bit more clever, and you can see, we've done a tab. So we'll go back. So this will put a tab. So the tab character /t will put a tab in there. I could have done. See if I get this. You could do a new line too. So they're just little secret characters. Put a tab in between your strings. Put a new line in between your strings. /n/t. There we go. This is a nice little construct for constructing arrays. Is the next one. So in Python, anyone used a comprehension before? Yeah, I got a couple of people. So I'll tell you the rest of you what that is. This is, you have this problem where you go like, I'm going to need an array and I know kind of just want to fill it in as I make it. This is a nice syntax for constructing this array in one go. What you can do is you can put a function in here. So say before I wanted to do sine 2 times /pi. So again, this LaTeX stuff, 2 times pi times x. Let's go I for I in 0 to 10. So what this would do is we've got an iterator on the back here. So there's from 0 to 10. I won't actually run this yet. I'll just show you what that does. This makes 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So back to this guy. If I go x equals I for I in 0 to 10, it will make an array. So did collect. That's a different way of doing it. It made an array that just pushes I in there. What you can actually do is put a function in there. So this is like really useful. So you can go apply this function to everything in the array. So I could go, for example, this one I was going to say, sine 2 times /i times I for I. And that's boring, and I hope you can see why, because they're all on the integers, so they'd all be close to 0. So if you wanted something a little bit more exciting, should go up and down. Plot x. Haven't defined plot. So again, import all these modules in Julia. If you want to do plotting, you have to import the module by using and wait for it to come through. And where did it send my plot? It's gone to somewhere strange. There. Oh, you get the picture. Anyway. Okay, so cool. So another one we can do, so for this example, coming up to the square root, so we can go I squared for I in 0 to 10. So we can square all these things, little caret to do the squared. Equivalent to going I times I, if you wanted to do that. This notation. So yeah, so this is useful. Another really useful thing that you can do is called broadcasting. So I don't actually like the syntax of this in Julia. I think it's a little bit hidden. You can do square root is a function in Julia. As I said, if you're never sure what a function is, do you help? It'll say what it is. Whoa. Oh, that's a lot of stuff. You get this impression that maybe it's a little bit complicated about what it's doing underneath, which is why we're going to talk about it today. So return square roots, throws the main error, lots of help. You can do square root on other things, which is a little bit of a hint about how Julia might work. Like, so say you broaden your concept of square root to apply to other things, like a mathematician might. Like, you might want to take the square root of, I guess, the square root of a matrix is what kind of thing you might think about. What does that mean? Depends on the actual object you're passing into it. So this is kind of getting towards what Julia does with type. But we're just working with like things that are pretending to be natural numbers, integers, real numbers for the moment. So we're just going to worry about that. So a useful thing you can do is apply this little dot, square root x, and they all come back. So just because I was waffling on in between that. So I've done a list comprehension, square brackets, I squared for I not R. And I want to take it back to what it was. I can do square root dot. What the dot will do will be apply the square root function to every element in the array one at a time. It's called broadcasting. There's other ways that there's a million ways to skin a cat. Like, you can do another way that's a little bit. I'll change the name of that because you won't know what the hell's going on. You can do a map, where it's like map this function over this thing. So basically equivalent, but nice little syntax. It's nice. I think it's not nice because it's hard to see the little dot, but that's how you do broadcasting in Julia. If the function works on the element of that array, you can apply it to the array. It's kind of cool. You can do it for your own function. So I can go function calls function x. And I can go return x 4 times x plus 7. And I could actually go calls function dot x, do all these things. So you can do it for your functions you define as well, which is super useful. Any questions on that? Just a little bit of syntax to get started. Everyone happy? Cool, I'll move on then. Okay. So let's go through some of this stuff. So 25, if I type who was paying attention yesterday, if I just type x equals 25, what's the type of x going to be as a default in Julia? 64-bit job. So how would we find that out? We go type of x, it's an int64. So if I go square root x, okay, you might notice something looks different about the way they're printed. Anyone notice anything? Might seem trivial, but sorry? Yeah, it's a float now. So if you want to know what it is, type of y is a float 64. So, you know, sorry. Gone off the bottom of the screen, have I? Is that better? Over to the right. All good now? Cool. Yeah, so type of y is float 64. So there's this thing, a little bit of magic underneath where it's gone, you know, what's the chance that this thing's a perfect square? I'm not going to bother trying to work out if this integer I'm putting in is a perfect square. Everything gets turned into a float when it comes out of the square root function. It's to do with how this is implemented. So that's cool. What do we want to say next? So yeah, that's pretty boring. So maybe not. Square root 2, square root. If I wanted to do 32-bit, you know how I was saying you had b and the x? What was the b for? Binary. X was for hex. F is for float 32, just as another one to add to your collection. So if I go type of hex, it's float 32. Sometimes it's useful to use float 32s if you're trying to save memory. Most of the time, for the type of stuff you guys are going to be doing, use as much precision as you can. Section 2, I'm going to talk you to death about floating point and what goes wrong with floating point. I find it interesting. Maybe nobody else does, but I find it amazing. Kind of fun. Okay. So if I do square root of x, I get, what's the type of this guy this time? It stayed as a float 32. So that's kind of interesting. If I put an integer in, it comes out as a float 64 as default. But if I put a float 32 in, it comes out as a float 32. So it depends on the type of the thing that's coming in, which is a big thing about Julia. It's like, you don't need to know it's doing this, and this is a useful thing it will do for you. And we can use this quite powerfully later on about like functions depend on the type of their input, the one that gets dispatched. That's what, if I say multiple dispatch with Julia, that's what it means. It means that it's a whole bunch of square root functions underneath, and the one that actually gets called depends on the type of the thing that's coming in. That's going to seem, why do you care about that? You'll see later. Just to bring it up early so you see what's going on. What's going to happen if, who wants to do a prediction, or who's read the notes? What's going to happen if I do square root minus 1? You could just do it, tell me. Anyone know? Let's see, an adventure. It's going to go domain error, because it's like, I'm trying to return a real valued thing, and you've given me a thing that's going to give me a complex argument. So you need to make a complex number. So Julia has a type for complex numbers. It's basically just sticking two floats together. It's a tuple of floats underneath, the real part and the imaginary part. So if you want to do that, you have to construct this thing. Complex. You can do it that way. I think you can also do it by going that as well. If you want to do it that way, you've got the im for imaginary. If you want to do that, you can construct it that way. Again, little thing you might have noticed, like there's a capitalization convention in Julia. Like when I did complex, it's not like a function. It's like making a type that's got a capital letter. When I'm calling functions, they're all lowercase. So for example, this square root is a function. I can get the help for square root like I did. Complex has a capital, and I'm using, that's a type. It's actually a type constructor, but you can get help on that. So complex number type with real and imaginary part of type T. Again, so you can get 16-bit floats, 32-bit complex float 16s, complex float 32s, and complex float 64s. If you want to go with that. So cool. So you can deal with this. You just need to be a little bit careful about the types. And this kind of method error thing you'll see where it goes like, I can't do that with this type. If you see method error, that's the kind of thing that you're trying to take. Let's do something dumb. Method error, you can't do square root of string. So if you see method error when you're mucking around, it's like you've done something that function doesn't support. Like you're trying to take square root of a string. But can't do that, not allowed. And it'll go, oh, you could do this thing that's either a float 64 or a float 32. You can do it with this mysterious thing that's saying it's to do with linear algebra or lower triangular. That's actually a type of decomposition of a matrix you might be interested in. Or you can do it with this uniform scaling, which is another type of matrix, where the idea of a square root makes sense. Like it doesn't make square root for a matrix doesn't make sense in general, but for these particular types of matrices, it does. Cool. Any questions on that? Has anyone got a method error yet when they've been playing around? You will. It's the most common thing you'll see is an error. It's usually what it means. So if you're starting to like debug through programs, you go, oh, what's going on here? Got this method error. That's a big hint about what might be going wrong. Cool. Yeah, I think I said all that stuff. Said about broadcasting. Yeah. Okay. So you might think, you know, if I'm trying to be clever, I'm going to go x equals 5.0. Like, how do we actually do square roots? I could do this thing. Oh, my 5 doesn't work in this thing. Square root x. But you will be sadly disappointed if you do this, because underneath the hood, it will be doing exactly the same thing. Julia will work this out and just be too tricky and go, haha, you're trying to do a square root. We're going to do it dispatch to the same thing underneath. So one of the nice things about Julia is you can find out how all this is open source, like the whole of Julia base is open source. You can go to Julia's GitHub. Julia language on GitHub. You can actually go and see how everything's implemented. You'll have a local copy of this, of course, when you've downloaded Julia, and you can go to all the functions and see how they're implemented. Like this is a crazy, crazy amount of people contributing to this thing. These top couple of people are the people who invented it. Jeff Bezanson is the first one, Stefan Kapitsky. Yeah, that's the co-creator of Julia language. They're all there. Yeah, so if you actually want to see how Julia is implemented, you can go and dig around and see how things are done. That's my point. Okay, so if you go into the source, I've got a link here. You can go, hopefully that link's not expired. We can go here and where did he say it was? 566 to 596. That's a long way down. It might be out of date. Of course, notes are out of date. Yeah, so Julia's changed under our feed. So function square root. So yeah, it's 685 now. We need to update the course notes. So hopefully it's the same. Yeah, so it's a little bit of, I showed this syntax yesterday. For the types of code you guys are going to be writing now, don't worry, you don't need to worry about this type annotation stuff. It's more when you're getting into this multiple dispatch stuff, you need to give it a hint about what types this function will apply to. You can kind of, for the kind of stuff we're doing, you can kind of leave it off and just let Julia figure it out. You don't need it for performance. You don't need it to make code fast. You just, when you're trying to do multiple dispatch, you need to do this stuff. Anyway, you can see what it does here. You're going to go, it takes an X that's a union type of float 32 and float 64. So if you pass it in a float 32 or a float 64, it'll go, okay, I'm going to try this. So this little inline thing here is if X is less than 0 of X, and then throw complex domain error square root X. So that's that domain error. When we tried -1, this first conditional got hit this short circuit thing, and it threw a domain error. That's that error you would have seen when it tried to do -1. That's what that code. Then you see this mysterious function called square root LLVM. So secret underneath all this, everything runs on this thing called LLVM. All these cool new programming languages like Rust, or I think Zig does as well, Julia, they're all really this other thing called LLVM underneath. You just turn in your code, gets compiled. In Julia, it's a just-in-time compiler. That'll come later. It gets turned into this stuff called LLVM, and that LLVM deals with running the code on different CPUs. So you don't need to worry about like it's going to run on a Mac or Windows or Ubuntu or different CPU architectures in every case. LLVM sorts all that stuff out, hopefully. LLVM is the low-level stuff working underneath. It's the stuff that's kind of talking at this logic level, like really, really low-level machine-level stuff about how do you do these things. So what LLVM will have is a specific, very fast, very clever implementation of square root. Julia farms it out to that, and that's what it gets the result back from. Cool. So this low-level virtual machine is a big project. I think it was by, I want to say Chris Latner. I'm going to be wrong. Yeah, Chris Latner. I think it was for Swift, for Apple, if anyone's done that one. But I think everyone's picked it up and run with it, because it's like you can make one of these high-level languages that use LLVM underneath to do cool stuff. So Julia is one of these ones. It's based on LLVM at the top. So that's this low-level virtual machine. You don't want to worry about logic and stuff. It's just high-level stuff where we're talking this human-level syntax that we can pipe down to low-level stuff to get things done. Yeah, so change to assembly code. So this is the stuff that's actually running on the CPU. So if you want to see what the LLVM code looks like in Julia, you can do this. You give it your function. This little @ thing's called a macro. So macro is like a program that writes programs. You think about that, it's like meta programming type stuff. You can actually see it's a macro that comes with Julia, and you can see what the LLVM code that gets generated looks like. So define double square root double blah, all this yucky syntax that's like all these strange little 4-letter and 3-letter things that are moving stuff around. You don't need to worry about. This is what low-level code looks like. You don't want to be doing that. You think about these people writing programs in, you know, in the 50s, it was all in assembly. Like, you don't want to be doing that. Maybe you do, it's kind of fun, but it's very hard to do anything useful. You don't even have for loops. So for loops are a construct in high-level languages. In low-level languages, you don't get that stuff. With low-level, I'm talking about like assembly. So you just get, yeah. So that's what it looks like in LLVM. Then for different CPUs, you can do, so again, so how this stuff gets implemented on an AMD or an Intel or one of those Cortex things, whatever they're called for Apple, will be different on each implementation. So you can see, if you want to see, I'm just on Intel stuff here, so you can see what the assembly gets generated for that, if you want to. So if someone's on a different CPU than mine, they'll see something different. That's kind of cool. You can see all this stuff. I don't think I've ever actually had to do either of these macros in my professional career on purpose. It's just a thing you might need to know at some point, but it's good to see what's actually going on. Yeah, so if we want to do it, I won't talk about big, that will come up later. I'll leave that one there. That's just like an example of doing a very big number where to the power of 100, how might you do that? We'll talk about that when we get to factorials, but I'll skip over that for now. So how do we actually do square root? So open to the floor. Anyone got an idea of how you might actually calculate a square root? Yep, that's like if applied mathematics 101, take a Taylor series, cut it off at one term, like it's linear, see what happens. That's pretty much every time. But interestingly enough, I was saying, like, you know, like people have wanted to take square roots. Oh, this is super interesting for me. I'll just go back. People have known how to, an algorithm for doing square roots for over 2,000 years. Like, this is pre-calculus. So this Babylonian algorithm is, I think it's like I think there's like some cuneiform thing where they've got a couple of digits of square root 2 written out, and somehow they figured it out. So they must have known this algorithm pre-calculus. So Taylor series, Taylor wasn't that long ago, he wasn't that old. And I think it was Heron had this actual formula here, some Greek guy in like the 2nd century AD. Yeah, so they've known about this algorithm for a long time. So this is a recursive algorithm, or recursive, this is defined by recursion. So we say, you know, the k plus 1 iterate equals half of the kth iterate plus z on x to the k. That's where what we're trying to find the square root of z in this case. It's super interesting that it's that old. I don't know how they would have figured that out pre-calculus, but it's like a lot of these things, it wasn't like it's just someone turned a switch and Newton turned up and then we had calculus. There were all these little hints on the way. It's not like one smart person did everything. It's kind of presented like that, but it's never really like that. There's a long history of this stuff. Cool. So we can write this out as explicitly as a loop. So you're going to see a bunch of syntax here. So for this, maybe I'll copy it and I'll just highlight bits as we go through. I'm trying to be conscious of this is going to have a bunch of new stuff. Just want to highlight parts of it as we go through. So we're setting up a function. We've given it a function named bab square root. So everything in the parentheses are the inputs to the function. Your first bit of weird syntax here is we've got this semicolon. So the way to think about that is everything that comes after this is an optional argument, like optional named argument here. So if I call this function and I don't give init x, verbose, or tol, it'll use these default values in the function. So like, if you don't want to be writing every time, tolerance, is that ever going to change when I call this function? I always want it to be some small number. Don't really care what that is. It's unlikely to change. You can have it as this optional argument. Then if you do want to change it, you can put it in later. It's a useful thing for making your code look a bit nicer from the API side. When you're calling this function, you don't want to set these things up every time. That's the first one. So it starts with the initial guess, what x equals init x, and we're going to have a while true loop. So this, be careful if you do this, because it might never terminate if you do this. So this is going to set up a forever loop while true. That's what it's doing. So true is always true. You're going to have to break out of that loop at some point to get out of it. So verbose and print. So this is this. You saw this in the LLVM in the implementation of square root in Julia. Had this short circuit evaluation. So verbose is a Boolean. So that defaults to false. So this guy is not going to happen. It'll skip over. If with this syntax, if this is false, it'll just skip over to the next line. That's what's going on. If it's true, and then it'll print line this Babylonian iterative. It's like, rather than going if verbose, println, blah, end would be the alternative. This is just like a compact representation doing that. Make sense? Yeah. Okay, cool. This is just writing out that funny Babylonian formula where we're going to go next x equals 0.5 times x plus z divided by x. Next x minus x is, so this looks at the absolute value of the difference between the iterates. If that gets smaller than tolerance, we're going to hit this break thing, which would jump out of the while loop. Then it will set x to next x and go. Yeah, so does that make sense? Any questions about that implementation of that function? Is there any weird syntax things there that I haven't gone through? Like silence is fine. So we can go square root of 2, and we'll go, hey, that did a thing. It was really quick too. So it's got this initial guess. We can probably break it if we do a really stupid guess. If I guess 1.4. Okay, so this is this optional argument thing. So like if I want to just set init x, I can do that by going like that. I want to set verbose equals true. Then it will go, okay, this is what it's actually doing as it goes through. It actually gets there pretty quick. So this is, maybe it's a really good first guess though. First iterate is z on 2, so that's 1. Then it's going to go to 1.5, 1.4. Didn't take many iterations to get there. Yeah, it's only like 5 or 6 iterations. So, oh, 1. Yeah, my 5 is really busted. I keep wanting to type 5. It doesn't want to do it. Okay, and we can compare that to the built-in one. So square root 15 is 3.8. And you'll see there's a little bit of fluff there on the last one. We do square root minus square root of 15. I don't know why I'm doing that. So there's this tiny number, 10 to the minus 16 difference. So they're pretty much, hang on, that's good, in 5 or 6 iterations. Cool. So I think we kind of jumped to the end there. Oh, Yoni's got a better first guess in the note. We've got a better first guess in the notes. We're starting with 2,500. Okay, so in case that wasn't clear though, just wanted to draw this up so you can see this. This is, as you said, perfect guess. It's like good guess is take a Taylor series, truncated it a couple of terms, set that to 0, rearrange the equation, and that's a Newton iteration. So that's what that's called, Newton's method. So this is like general procedure for finding zeros, really useful thing. Who's done this before, who has really good intuition? How can we break this? What's the way it could go wrong? Very wrong. Slope is 0. Yeah, that's one. What will happen with our function if our slope was 0? Probably help if I show the. Yep, that's good. Perfect answer. How could you guard against that? Yeah. So that's kind of like, it's like regularize it. You can make sure it never gets below a small value. Then you're never going to have that problem. What's another way it can fall over? Anyone else got super intuition? Let someone else have a go. Yep. So you have to speak up. Fall into a loop, yeah. So you could be outside the radius of convergence of this thing. So it's not guaranteed to converge. Like you could have a really wacky function, like square, like this is I'll probably draw something like a square, but the wrong screen. You could imagine if you had some horribly complicated function, you know, struggling to draw. Well, oh well. Anyway, you get the picture. You had a weekly function and you pick a bad starting point. You can cycle forever. This is a thing that can totally happen. You also have just a really stupid first guess. So, which goes to how can you make it fast? The opposite side of that is like, just guess the answer and you're done. So this is a common problem. So it's also common in applications to want to find the zeros of a function. Much more common is to find a minima of a function. Like if you're thinking about a practical problem, like where Andy's coming from, where he works for a company that does optimization for businesses. So you set up like a mathematical model for a business and you're trying to find what's the ideal operating point, you know, given all the levers that a business has access to. What's the minimum? Or you've got a machine learning problem where you're going to go, I'm going to try and find a function that represents this arbitrary data as accurately as possible. I want to minimize some error metric. You're actually trying to find a local minima or a global minima, hopefully. So it tends to be the second order version of this where you're trying to find a zero order derivative. So you're going to try and go to the bottom of the hill rather than find a root explicitly. And you have all the same sorts of problems where, you know, having a good first guess is really important to get the method to work. You can have these pathological cases about what the derivative is doing, whether it's stable or not, especially when you've got second order terms. Yeah, that's cool. So cranking through the maths, as I said, like you just do this, as I tried to draw here, you just take a Taylor series of this function. That's the derivative term. You're going to try and find out where it equals to 0. This is the basic Newton iteration. Then you reset the function value to that value of x. These are these iterations. Take the slope again, solve for 0, and hopefully you sneak up on the root of that function. That's basic understanding of how that works. And that's that rearranging of the Taylor series. You apply that to the square root function, you end up with this Babylonian average. So somehow some person very smart or really good at guessing came up with that 2000 years ago without knowing calculus. It's like makes my brain explode somehow. It's really clever. Okay. Any questions on that bit so far? So this is one way of taking square root. Again, it's not how square root is actually done. There's much faster methods now that are very complicated. You can go and look at the Wikipedia page. You'll see like a dozen different methods for calculating the square root. As I said, this one, though, much more common to want the reciprocal of a square root in practice. For me, this is one I've always had to do. Anyone think about why this might come up? Normalizing vectors. This is usually one. So one that came up for me a lot is doing geometry. So I've done a lot of work in remote sensing where we take a LiDAR scan, which is like a laser rangefinder. You fly it around on a plane or put it on a car or something. How far away is everything in the room? And you get this map of points. And then you might be interested in making something like a surface from the points. So you might want a normal vector from that and then do some calculations with that. That's one where you want to keep renormalizing these vectors. So don't know if we saw it, but like, I think some of you have seen it in you were talking to me after the lecture last night, like floating point error we'll talk about coming up. You always get this little bit of fluff when you're doing calculations of floating point. They're never 100% accurate. You always get this little bit of little epsilon of error every time you do these operations, and they build up and build up and build up. And what happens is you end up having to renormalize vectors that are like, it's a unit vector. So if it's non-unit, like if you sum up the norm, you go, oh, it's bigger than 1. Damn it, I have to renormalize this vector and start again. And that's something you end up doing in algorithms really commonly. So this, yeah, so got some examples here of how you might normalize a vector. This is kind of an infamous one though. Who's heard of the fast inverse square root algorithms? That depends how nerdy you are. You know it? Yeah, it's an interesting thing, and I kind of like showing it because I was talking yesterday about like software is about communication, and you guys are all really smart. You can be a bit too smart, and people can get really confused. And this is a perfect example of it. The game, I think it was Quake 3. If anyone's played Quake 3, if they're old, that got released to the open source. It got GPL'd, so everyone could see it, like early 2000s. And one of these, this was kind of wonderful thing came up of like, it's got float q r square root. So I don't know why it's got the q, but it's like reciprocal of a square root. This is in C. Can anyone read C? I said till one person stick their hand up saying they could read C. No. Well, a little bit. We've got this type stuff. We've got long and float. So this is like in C, it's like, you know, is it a, like what size integer is it and what size float is it? Is it, you got double and a float, float's 32-bit. Yep, that's an integer. We're setting up some constant float, 3/2, blah. And then there's this mysterious thing, and you can see some comments at the side that other people saw here. This line in particular is super mysterious. And we've talked about types, so I think this is really interesting. I'm going to say, I've written what the Julia equivalent code is below this, just so it's a bit easier for you guys because you're learning Julia, you don't have to learn C. And then there's this other that's got this, we've boulderized it here and cut out the actual comment, but it's very confusing about what it's doing. And then we see they're talking about first iteration, second iteration, and this thing is a comment. So in the code, this bit isn't actually evaluated, that bit's like not run. So they've went, we do 2 iterations. Oh, we didn't actually need to do 2. One's good enough. So this reciprocal of a square root came about in Quake. In early computers, much more limited hardware. I was saying, like when I was a teenager, it's like megahertz, not gigahertz. So being super efficient on these sort of low-level calculations for doing something like a 3D game were a big deal. So this is like a super optimized version of doing this reciprocal square root on the hardware of the time. Equivalent code in Julia. So this is this line here. This is where they're saying evil floating point bit level hacking. There's this function in Julia called reinterpret. Again, if you're ever confused, reinterpret. Okay, change the type interpretation of binary data to the primitive type, in the primitive type A to that of the primitive type. Anyone want to, so I've said, I want to take a number that's coming in as a float 32, and I'm just going to take the bits of that and then pretend it's float, then pretend it's a uint 32. That's confusing as hell, right? Is that clear to everyone? A bit lost? So as we said yesterday, so if we have a number, so we were talking about the bit level representation of uints and signed ints yesterday. There's also a bit representation of floating point numbers. It's very strange to take a bit level representation of one type of number and then pretend it's another type of number. Like for signed integers, it makes no sense. Why would you even do that? This is to do with the particular representation of floating point. And your floating point is, you can think of as like scientific notation, like, you know, 1 times 10 to the 3, but for binary. And you just keep the bit out the front and the exponent bit and put them together. And that's what the floating point is in binary. So this interpret doesn't really make sense. Very confusing. And then there's this, they've taken an arbitrary, remember what was the X for? Anyone remember? That was for what type? Hexadecimal. So they're saying there's this big hexadecimal number, 5F3, blah, blah, blah. It's a magic number. And then we're going to go, once you've reinterpreted this, we're going to do a bit shift one to that direction, to the right. So what was that? Bit shifts were like divide by two. So this is super confusing, right? So take a number that's a floating point number, reinterpret it as a u-end, bit shift that number, divide it by 2, and subtract off this random number off the front, and then reinterpret it back into a floating point number. Super confusing. What that turns out to do is that's just a way of getting a good first guess for Newton's iteration. So that's because it's like scientific notation. If you take a floating point number and you reinterpret it as an int, it's kind of like taking a log. So if you go send through the crank, you got 1 on square root x. If I take the log of that, it's going to be like, 1 minus 1/2 times x, So hopefully you go through that and then you go, that's kind of what this guy's doing. That 1/2 is the bit shift. And then this is to do with the specific representation in floating point. Whoa. And then you do one iteration of Newton's thing. And so we've shown a little example here that this is like, it does a reasonable good job. If you do 1 on square root 4, it comes out with a number like 1/2. Whoa. Okay, what's my point in showing this? It's like, you can be too clever and you can write terrible code. Some people will think you're really clever. Like lots of people idolize this. They actually misattribute it to John Carmack, who's like the guy who wrote Doom years ago, kind of a famous programmer. Misattributed to him. It's actually a really old method that goes back to the early days of computing. I think the guy who invented MATLAB has something to do with it, Cleve Moller, bizarrely. Yeah, and then I think there's some good histories on this. You can go look around, but this thing of this magic offset is a particular for float 32. If you tried to do the same thing, float 64, you'd come up with a different offset because of how their floating point numbers are represented. And you can actually, these days, like, this was very clever to come up with this in the 90s. This is how far computers have come. We're saying, like, how many 32-bit numbers are there? There's like 2 to the 32. You can actually brute force this these days to come up with a better number. Back in those days, they had to just have a guess about what would be the ideal offset, but there's actually a slightly better one, I think. Don't take my word for that. Anyway, my point with this is you can be too clever. This is all comments that people wrote after the fact. So someone else was going through this code and going, what the hell did this person do? I don't understand this at all. And they've tried to have a guess about what's going on. And it's kind of an example of like being a bit too smart. Like when you're doing your homework, when you're doing the big homework, just trying to get the answer and you kind of worry about lose sight of comprehensibility. Don't do that. Come back to it later on once you figured out how to do the problem and make it nice so people can actually read it and understand what you've done. There's no point being clever if people can't understand what you did. I think that's my point of doing this. As I haven't talked to you too much about floating point representation yet, I don't expect you to follow that completely. It's just a nice thing to see. Interesting example of how you calculate these things, how you used to calculate these things as well. It's actually changed with hardware gotten better now. There's actually much better ways to do this now. And there's a link here to a YouTube video that I think does a really good job of explaining it. So I'll outsource that to some random on the internet. If you want to go through and learn a little bit early on about how floating point representation works. It's a good primer for when we get into section 2. Okay, all right, nearly 7 o'clock. I think that's a good time to stop. We're getting up to factorials. Have any questions on that stuff? Any questions in general? If you have any questions about homework or anything, I'm happy to hang around. Thanks, everyone.